Getting a PLC timer to run once is easy. Getting several timers to run in sequence, turn their output off at the right time, and then automatically start the sequence again is where things get interesting. In this video, I'm going to build this sequence from the beginning, and along the way, we will solve several common timer problems that can make the sequence fail. When I press start, the red lamp runs for 2 seconds, the yellow lamp takes over for 3 seconds, the green lamp runs for 4 seconds. Finally, the sequence resets and starts another cycle. And I'll show you how you can stop the entire sequence. Let's start with one timer. Here, M0 is used to activate T0. The preset is K50, representing approximately 5 seconds in this example. Once T0 reaches its preset, its contact changes state. We can use the timer contact to control output Y0. So, the basic operation is straightforward. Activate T0, wait for the preset, and then use the timer contact to control the output. But now, let's consider the actual start signal. The push button we are using is momentary. That means X0 is on while the button is being pressed. If I press the button and release it before the 5 seconds have elapsed, the input goes off. And because of that, input is also a condition controlling the timer. The timer loses its enabling function. For a standard non-retentive timer, the timer will stop and reset when the enabling condition goes false. So, T0 may never reach K50. So how do we solve this non-retentive timer problem? Instead of asking for the push button to hold the entire sequence, we use an internal relay. Here, M0 acts as a holding relay. When I press X0, M0 becomes active. The M0 contact then creates a holding path. So, when I release the push button, M0 stays active. This gives us an important distinction. X0 is a momentary command, M0 becomes the maintained condition that holds the sequence. Now we need to understand what happens to the timer contacts. A normally open timer contact is open before the timer reaches its completion condition. When the timer reaches its preset, that contact closes. That makes it useful when we want an action to occur after the timer has completed. A normally closed timer contact behaves in the opposite way. Before the timer completes, the contact is closed. When the timer completes, the contact opens. And that normally closed contact is going to become very useful for our timer outputs. But before we use these timer contacts, there's one behavior you need to understand. Look at this normally closed T0 contact. The timer hasn't been triggered yet, so T0 is not complete. That means its normally closed contact is closed. And because that contact is closed, Y0 can be energized immediately. So if you ever see an output turn on before your sequence has started, don't immediately blame the timer. Check the normal state of the timer contact you're using. We don't want the timer's normally closed contact to control the output by itself. M0 first establishes that the sequence has actually been started. The normally closed timer contact determines whether the timer stage is still active. The output is now controlled by both the sequence command and the timer state. Now let's turn this into our first stage of our actual sequence. M0 activates T0. Here, T0 uses K20, which represents 2 seconds in this example. The red output is Y0. The normally closed T0 contact allows the output to remain active while the timer has not yet reached its preset. Once T0 reaches the preset, that contact changes state and the red lamp lights up. Now let's move on to the second stage. Instead of allowing T1 to start independently, we connect it to the completion timer of T0. So T0 becomes the condition that enables T1. T1 uses K30, which is 3 seconds in this example. Its normally open contact is used for the yellow output Y001. This is what gives us a true sequence. The second stage cannot begin until the first stage reaches its required condition. We use exactly the same principle for the third stage. T1 completion enables T2. T2 uses K40, which is 4 seconds. The normally open T2 contact controls Y2, our green lamp. So now we have 3 timed stages linked together. Now we have another problem. The sequence reaches green and stops there. We don't want to press start again every time. We need the ladder to return itself to the beginning. This is where the final timer T3 comes in. When T2 reaches completion, it activates T3. T3 uses K50, which represents 5 seconds. Now add the normally closed contact of T3 to the T0 starting circuit. This contact is what will allow us to interrupt the first timer and prepare it for another cycle. While T3 is active, its normally closed contact changes state. That breaks the enabling path of T0. Since T0 is a standard non-retentive timer, removing its enabling condition resets its accumulated timing. When T3 reaches preset, the normally closed contact returns to its normal closed state. T0 is now able to start again. With our loop sequence now working, I want you to observe the state of our outputs in this sequence. Once a timer proceeds to the next timer, it leaves the previous output active. To have it trigger only one timer at a time in a sequential manner, replace the normally open contacts of T0, T1 and T2 with normally closed contacts. Update and write the logic to the PLC. Now when I press start, M0 latches, T0 begins the first stage. The red lamp runs for approximately 2 seconds. T0 then enables T1 and yellow takes over. After approximately 3 seconds, T1 enables T2. Green now takes over for approximately 4 seconds. T2 then starts T3, and once the loop stage is complete, T0 is ready to start the sequence again. And the cycle repeats automatically. Now, if your version of sequence isn't working, here's where I will start troubleshooting. First, check whether M0 is actually staying on after start button is pressed. Second, check whether the timer you are expecting to run is actually receiving its enabling condition. Third, check the timer contact you are using, especially whether you've chosen normally open or normally closed behavior for the results you want. And finally, check the transition from one timer to the next. If you're learning PLC programming, don't just learn how to write a ladder. Learn how to understand what the PLC is actually doing when the sequence doesn't behave as expected. That's what I share here at Bob Teaches Tech: practical PLC programming, industrial automation, and troubleshooting. Subscribe for more hands-on tutorials and visit bobteachestech.com for additional technical resources.